All right, we seem to have stabilized in size. I vote we get rolling because I'm excited to hear it, if nothing else. So it is my great pleasure to introduce Professor Robert Axtel to give our keynote talk at CSS 2021. He is a whole slew of things that I'm probably not even going to get all of. But he's part of the Computational and Data Sciences Department. He runs the Computational Social Science PhD at George Mason. He's also affiliated with the Department of Economics. That was news to me. And the co-director of the Computational Public Policy Lab and the SCAR School of Policy and Government, which I'm sure I mispronounced. He's external faculty at SFI, which is great because it gets him out here periodically. And he's also external faculty at Northwestern, their complex systems group or institute. And he's on the Scientific Advisory Council of the Waterloo Institute for Complexity and Innovation. And I would be willing to argue that with Josh Epstein, he wrote the book that got us all going in all this, the Growing Artificial Societies, back in 96, I think, 98, maybe?
Six,
yeah. So 25, well, more than 25 years strong now. He's also now going to be on sabbatical, so we're lucky to have gotten any of his time because it seems like Rob gets busier when he's on sabbatical. And he's also a Google faculty scholar now, which is cool. And as I understand it, he knows his way around a small block engine, which is sort of fun too.
Actually, so, big block Chevy. Yeah.
Oh, big block. Sorry. I clearly do not know my way around an engine, internal combustion or not. And so with that, I'd rather stop talking and turn things over to Rob. So please take it away. And just so folks know, we are recording this session, which is unusual. We don't typically record things at a conference, but we do tend to record our keynotes because they're typically really fantastic.
Okay, well, you set a high bar for me on that one, Matt. So I'll live up to it here. But great to see you all, and thank you for the invitation to speak and for the warm introduction, Matt. Thank you very much. What I'm going to talk about today is work that many of you guys have seen parts of before. So I think that in some sense that part will be things that you are somewhat familiar with. But it's I have to say that over the last year or so, a year or two, working with Omar Guerrero on a big project that I'll talk about. We've come to think about it in a little different way than we have before, and so I guess the main kind of the wrapper for this talk is at the front end of the back end of this talk is this idea of what does it look like to build models in the social sciences broadly construed using computational tools, but that are that really have a ton of data. I mean, are these just models in the usual sense, or are these a different kind of model? And in particular, so the title, which I think that Matt has helped me come up with here, Sensemaking at Scale. The idea is that when you can do things at very large scale, the question is, do you get different classes, different kinds of models, results, just different kinds of science than you would otherwise. And so I'm going to try to make the point that it seems to me anyway, if you're thinking about this for a fair amount of time, that it does feel different. And so here's the way we're thinking about it. So if I can advance these slides here, let's see, go like this. All right. So you guys all know this, but it's just I'm going to just kind of summarize the idea that the amount of data available to us is unprecedented now in the last decade or two compared to before. So at George Mason, Vernon Smith won the Nobel Prize in 2004 or 3 or something right around then for basically laboratory experiments. And so being able to see what people do in kind of competitive settings or game theoretic settings in the laboratory is a way to get data. But this is really typically small scale data. And the big data comes when we think about can we do experiments online? And so some of you know the work of Damon Centola. He has a couple of books out, but his earlier he had papers in Science about doing health experiments with on the order of thousands of people online. And then in the last over the last couple decades again, economists have done randomized field trials. And by the way, let me just pause and apologize that there's a fan in my hotel room that comes on periodically. I think it's going to be on for on for a couple minutes and off for 10. So hopefully it won't be too disruptive. It's just kicked on now. So for the large randomized field trials, some of you will know Esther Duflo and Michael Kramer and others won the Nobel Prize a couple of years back. Another way to get big data available, to get large amounts of data available. And then, of course, there is this what Duncan Watts has called digital exhaust, which is this is going to be now, the big data companies have data, yes, but they oftentimes just have this kind of side effect data. That is, we query this website, we buy this product, etc. They collect, kind of the remnants of that, right? They don't always know why we did something, but they know what we did, and they have this kind of you can't really tell where the car is going by looking at its exhaust, but you can tell how hard the guy has the gas pedal pushed down, etc. By looking at the remnants of the combustion. So I think this is an apt metaphor and another way to get large scale data, which I personally don't know a lot about those kinds of data, but I'm hoping to learn some in the next year or so. Finally, I'm going to be talking today almost exclusively about administrative data. These are data that have been collected typically by government or other kind of regulatory agencies, that some kind of body with the right to collect the data. But I think the key idea is that oftentimes these data are comprehensive. So think like Social Security Administration. They have payroll data on all Americans who ever expect to receive Social Security in retirement. Think about the USDA. They have data on the kinds of food that's purchased by people who receive the Supplemental Nutrition Assistance Program. And then I'm going to be talking specifically today about data on taxes, tax return data. And but the key to that is that it's at least notionally comprehensive. That is, it's almost at full scale. That is, yes, there are maybe some firms that are not in the data, but those firms that are operating in the black economy and presumably are not that large a part of the economy. Anyways, this is all brought together, of course, because we can do large scale computing. We can really represent whole systems, whole societies, whole economies. I'm going to show you such a model today. Some of you guys have seen that before. But anyways, without the large scale computing, obviously, there's no value to the big data. But with the large scale computing, we can do things. Now, one corollary that I've been kind of discussing a lot with my students is that there is so the good news is that we can move beyond very simplistic models of representative agents, one agent, one small bit of data, etc. But I do have the following concern a little bit, is that what can we do in the year 2021 here that is going to be of interest to people in the year 2040, when they're going to have on their machines a lot more capabilities than we have, or in 2050 there's going to be 100 or 1,000 cores in every laptop. I mean, I just saw that the new Mac laptops have 64 gigabyte of RAM possible, and you can get a dozen cores. It's not going to be that long term. You're going to have thousands of cores available readily on a modest size machine. And what can we do today that's going to be of interest to those people with such elaborate computing technologies? But anyways, we'll come to that at the end. So the basic idea here is as follows: is that I want to suggest that what we normally do in particularly the natural sciences is we understand the basic structure of what we're looking at, and at the margin we're adding a little bit of more knowledge to this. So this is what Thomas Kuhn called normal science. Right? We know what the tiger is. We know it has 4 feet and the stripes, etc. And we don't know maybe the extent of its tail or how much air it breathes or something. We can add more data to that scientific picture over time. And this is normal science. We're not talking about kind of redoing what our basic understanding of what a tiger is when we do research on tigers. And just to give some evidence of that, I mean, I just pulled this from a week ago. There was some article in realclearscience.com or something about there's some new result in the Large Hadron Collider. It may give us. It may challenge the standard model of physics. So the standard models, like the tiger, right, is something which has high accuracy, and we understand what it is. But the question is, does this new result possibly support the idea of some new physics? That is, for decades now, physicists have been looking for is there any kind of new physics? Is there something that we don't really understand? We understand the basic structure of the whole thing. What is there something that we don't understand? And I just would like to kind of compare this view of like, normal science, add to the standard model, learn something a little bit more about the tiger by doing research on it, by saying, how does that really compare to the current world of the social sciences with the great inundation of data that we have going on right now? And so to frame this, I want to pull up a specific version of the philosophy of science that some of you are familiar with, I know, but not everybody is. So I want to go through it in just in a bit of detail. That's that. We typically have some real social process under study. It's a market, it's a firm, it's some social media thing. It's a national defense topic, something. And then we have some theory for how that thing works, right? I mean, it's a market. We know the purpose of traders; they don't want to lose money, whatever it is. We know it's a firm. It's making products. Has a CEO. So there's some theory of how the social process works, and the glue between these things is, one conception anyway. It's basically going to be that there's a model, right? And what the model does is, we don't actually have the entire social process to look at. We have only the data about the social process. So we have some pull of data from the actual social phenomenon under study. And then the theory can be instantiated for that particular thing we're studying. So it's a theory of markets. We're going to look at the New York Stock Exchange as the actual phenomenon. Well, let's instantiate that with there's going to be only 1,000 issues trading hands. There's going to be 500 specialists on the floor, or whatever it is. And so the glue between these things is the model. All right. And so this particular this is not quite Karl Popper's view of falsification. Rather, this is what's called the models mediate theories in the real world view, due to Mary Morgan, Margaret Morrison, and you may also know the name Nancy Cartwright. So these are philosophers of social science at the London School of Economics. And they have really pioneered this idea that models as mediators, right? Models are the thing that make the data from the real world talk to the theory. And we have a theory of what this, of the standard model in physics. We get some new data from the Large Hadron Collider, and they're going to collide when we build a numerical model of what should have happened versus what did happen. Or it's a model of we have a theory of markets. We have a theory of firms. I'll be specific now. We have a theory of how firms behave, or theory or theories. We have data about what the firms actually do, and now we're going to use the model to adjudicate that medium. And so what I'm going to now assert, and then try to get you guys to believe over the next 40 minutes, I'm going to assert that basically this particular picture works well for the social sciences, works well in the natural sciences. But what's new and different is, as I mentioned earlier about all the data, are that what's new and different is that we have such an inundation in data that, in fact, it may be that many of what we think are the valid theories in the social sciences are not going to stand up to the kind of data we are getting. And so we're entering this new world, this brave new world, where there are so many data that, in essence, this is going to be my punchline at the end. That basically all social theories are false. All social theories are today falsified in those domains where we have huge amounts of data. And now, just in talking to everybody before my remarks began, it was mentioned that there are several domains. Maybe the MITRE guys, the RAND guys have experienced it, where data, getting sufficient data are the bottleneck. But there are domains also where we have all this data, and basically what the data do are they falsify every existing theory. Now I'm just going to give you an example of that. I'm just going to give you a very concrete example. Once again, some of you guys have heard me talk about this, but I'm going to go through just maybe a little different emphasis than before. So when it comes to why we have firms, what firms do, how firms operate, we have this kind of economics 101 view of a firm as being firms just maximize profits. And this is due to Alfred Marshall at the turn of the 19th to 20th century. He formalized this quasi-mathematically. It's still taught to undergraduates. All of us have experienced this in some way, shape, or form. But in fact, it was a different view that won the Nobel Prize. And the Nobel Prize for the theory of the firm was awarded to Ronald Coase, because Coase said, well, there are two lawyers sitting in adjacent offices running their own business. Are they each trying to profit maximize? Well, maybe. But then what if they both need secretarial help, or they both need to have access to the same law journals or law books? Could they economize and form a firm to get rid of transaction costs associated with maybe sharing a resource or something? So the idea is a firm A firm is not a market. Firms live in seas of markets, and how does all that play out? Transaction costs are one answer. But then game theory came along, and game theory said things are richer than that. And in game theory, we really have the idea of a firm where a few of us may own the firm, and then we hire some other person to run the firm. So we are the principals. Then we hire this agent to be our operator. And so this involves contracts and involves game theory, and that's a different view of the firm. And then all the top three versions are really what are called non-cooperative theories of the firm. That is, there's some kind of competitive relationship, but it could also be the case that a firm is going to be a bunch of people who are cooperating. And so there's in what's called cooperative game theory, there's something called coalition formation models, a different version of why firms work. And then some of you will know there's an old book by Marshak and Rader about team production. Basically, the firm is a giant team. Their view was that everybody has the same kind of utility function in the firm, and then the question is, how can you get good results to happen? A sidebar on that is that there's increasing returns to scale. That is, people can accomplish more in groups than can as individuals. So the team production version. Law and economics is the one that plays out in the antitrust courts, right? When firms want to merge or firms want to spin off, is going to make the markets more or less competitive. That's something that the Department of Justice cares about. More recently, in the late 90s and early aughts, there arose the idea that firms can be arranged in different kind of network structures. Maybe a firm is just a giant communication network, and it only gets as big as the communications are coherent. And as soon as the network is too big or too noisy or whatever, the firm can't grow any bigger. So there's actually, some of you may know, there's a version of why is Walmart able to do what it does? Well, it actually has very interesting non-trivial communications from the local stores up to the headquarters in Arkansas and back. And so firm as network is a modern perspective you'll find in business schools. And then, of course, there's this older one, which I'm going to associate with a name that you all recognize in a minute. But organizational models in economics have been around since post World War II era. It is organizations are really organizations. Firms are organizations, yes, but then there could be things like organizational identification, et cetera, operating rules and things like best practices, et cetera. And then finally, there's an entire theory due to Nelson and Winter, and every year we just get been through Nobel time. So every year at Nobel Prize time, Sid Winter and Dick Nelson are on the short list for people who might win the Nobel Prize. Their evolutionary model of firms. They say, firms cannot profit maximize. Firms are more than just principal agent problems. So they say, really, firms are these that are adaptive. That is, a firm over time will change the markets it's in, change the way it operates, et cetera, et cetera. We need to be cognizant of that. So with each one of these theories of the firm, there is associated kind of a school of thought associated with names. So the second one, Coase and Williamson, both of those men won Nobel Prizes. Lafont won a Nobel Prize for the work on principal agent problems. Holmstrom shared the Nobel Prize with Oliver Hart for team production models, et cetera, et cetera. So every one of them, and then with the organization theory, we have Herb Simon and his co-authors. I mentioned Nelson and Winter, but also Alshian at UCLA. Okay, these are all distinct theories of the firm, right? These now, if you do industrial organization, you have to kind of keep at any one time in your head all of these competitive theories. They have, they say some things in common. They have some things that they say differently. Here's my immediate question though for you guys, having just had the earlier slide about how many data there are. What do these individual theories say about what the microscopic data should look like on firms? That is, if I were to give each one of these researchers all the data, what would they be able to suggest that their theories limit the data? That is, what kind of constraints on the data would we expect to see given the fact that we have these theories? Maybe a slightly different way to say the same thing is to say, if in fact we could adjudicate between these theories, if these theories are not all equally true, but some are more useful than others, some are more scientific than others, could we adjudicate these by saying which ones can explain the data best? And what I'm once again, the punchline on all this, which is not going to be, it's not, I have to now proceed with kid gloves if you guys were economists, but the punchline on all this is that none of these theories do a very good job on the data. And in particular, now here's a stronger way to say it is, none of these theories can explain more than a tiny fraction of the data. In fact, most of them can explain none of the data. So, and I'm going to raise the question as social theories, because these theories cannot explain the data. Are they really scientific theories, or are these kind of more like philosophy, almost some kind of philosophical theory? That is, they're plausible. They're kind of like we all know that there are various competing theories of physics, right? There's the or think about Grecian chemistry as just an extreme example, right? In Grecian chemistry, there's land, fire, water, and air, or something, right? The four elements, right? Today we have the periodic table, which is richer than that. I mean, the Greek theory of chemistry is wrong. I mean, to put a coarse spin on it. And I mean, is it the case that these theories now here, because they cannot speak to the data, are they in fact do they have the same qualities as kind of Greek chemistry? And I think that modern economists would say no. We learned something from these theories. But at the end of the day today, I'm going to say, once again, the suggestion for the talk is when we go to scale, when we use all the data, when we build models, maybe elements of these theories are useful. But in fact, if none of these theories can explain the data, are they in fact scientific theories? So we can discuss that at the end. All right. What I'm going to do now is, and I have a lot of slides to go through. I'm not going to go through all of them. I'm going to just burn through some of them. What I want to basically go through is just, we're going to do this now for firms. We're going to say firms are the domain where we have a ton of data. And this is where many of you guys have seen large swaths of this before. But the idea is that we have this microdata on all firms by sizes and ages, say, just to start with. And then, of course, we can do fun things like we can slice and dice these things by the way, the sizes come in different metrics. What are the receipts? What are their market capitalization if they're a public firm? How many employees they have. But we also know the ages of these firms because we know when they first asked the IRS for a tax number, and we're getting the data from the IRS, and so we're going to basically have a very crisp demarcation of when they were born, when they die, also. But we can, once we have sizes and ages, we can start to slice and dice. We can say, what is the age conditional on size? We can say, or what is their size conditional on age? What are the receipts conditional on age? What are their employees conditional on age? So you can do a lot of stuff with kind of iterate. Remember, the law of iterated expectations can play a big role here, and you can do a lot of fancy stuff there. But then productivity is just really output per unit of input. Well, output is a size distribution, input is a size distribution. We can do this now. Now we can slice and dice this by age and size, etc. And then growth rates. Growth rates are just changes in size, okay? But the main thing to say about all these data, employment and job tenure, how long do people stay in their job? And then networks. I'll show a couple network pictures today. The main thing to say about all these things is we are not going to run regressions on this, which is the normal procedure where you have all this ton of data. Rather, we're going to say, let's take all these, let's look at all these data in their raw form. Can we tease out gross regularities or patterns or some kind of a structure from these data? And then the question is, which of the theories on the previous slide can tell us anything about these data? And once again, I want to state the point baldly, without any disrespect to the people who came before who wrote those theories, because they did not have access to these data. Okay, I'm sure that if they had access to this data, we'd be a lot further along than we are. They did not have the data. There's no way we could expect them to ever predict or forecast what the data should be. But the bald way to say it is, none of those theories tell us anything about any of these data. Okay, I'll say it again, right? That the theories are impotent when it comes to the data. It's just simply irrelevant. Okay, so here's now the picture. Before I showed you the picture of the tiger, and I said, the normal science adds to the tiger. It shows how long his tail is or whatever. Here now, the upper left-hand corner is meant to be, we're swimming in data. We just, somebody dumped a puzzle box in front of us where they said, here are 1 million pieces. Call us later when you have the thing built. And the answer is, the lower right-hand corner says, we don't have very much built yet, but we got some of it. Okay, we've been able to, the border pieces are square, I guess. So we found those border pieces, and now we're going to basically start filling in the picture. What does our tiger look like? Well, today, not much. We can't tell you much about what do firms really look like? Which models can explain the firms? And the answer is, I'm going to show you the results, but they're going to be quite preliminary. Okay, so I'll come back to that at the end about saying we have only preliminary results. Okay, so with data from administrative sources, and importantly that it's comprehensive, so we're not missing anybody. With the usual caveats about privacy concerns, that I'm not going to show you individual records, I'm going to show you bin data. We're going to start building models, and models have some sense that they could be machine learning models, they could be representative agent models, they could be models with continuum of agents, and that is kind of mathematically fancy models. But of course, you guys knowing my work, you will say that it's going to be computational agents. And let me just also mention that Matt mentioned that it's the 25th anniversary of the Epstein Axtel book, and let me just say that of course that book also uses computational agents. But then, what does that book have in common with what I've said so far? The answer is, obviously the social science perspective adumbrated in that book is not about data. So I think it is the case that the thing that all of us have lived through in the last 25 years is this basically mixing or meshing of agent technology as an AI technology with all these new data. And so, I also mentioned this at the end, but we are living through a literal revolution where we're doing things that are very. I think that all of you guys are doing things that are very foundational and will be critical for how we do social science in the future. And the late 90s gave us the technology, the computing techniques for doing it. But only now can we really bring the data to bear on the models and really understand how the models can be made into scientific instruments of the same type that Galileo fashioned the telescope and revolutionized astronomy. I think we can do the same thing with data plus computing. Okay, and then and a live way to say this, to make the point I just said was, every one of the models that we build has some number of dimensions that we care about. Things like how many agents, what beliefs do those agents have, are they strategic agents, yes or no? How do they behave, etc. So for every model we build, we have different dimensions. But in the social sciences, we have to care about what are the institutions, how do the agents interact, etc. And then in this middle column here, so hopefully you can see my mouse. In the middle column is really the kind of the approach we take to do, in essence, kind of the mathematical social sciences. So if you do microeconomics, or if you study kind of these days formal political economy, game theoretical economy, even allied areas like in sociology, there are, when you do formal mathematical theory, etc. We don't know how to make progress in general with real social phenomena consisting of 10,000 agents. So we'll say, let's look at a representative agent. Let's say that all the information is homogeneous, so that agents have homogeneous beliefs, etc. We may be in a decision theoretic or game theoretic environment, but basically it's going to be solving for rational agents. What's the best thing to do? Now, this is taught today, and this is the normal way we do things in academia. Not because any of us really believe this is how the world works, but because this is all tractable, right? We know how to solve for Nash equilibrium. We know how to do optimization calculations, et cetera, right? So we don't know how to model institutions, so we don't give we give short shrift to that. And so, but I think that what's coming on the horizon here, and what people like Brian Arthur and Dawn Farmer at Santa Fe have pioneered, but before them, Herb Simon certainly articulated, is this idea that, well, there is a complexity view of the social sciences, of economic models in particular, where we want to have behavioral agents, right, who are going to interact through networks, and they're going to interact not just in equilibrium, but also dynamically. And there will emerge macroscopic structures that are not coded in. We don't code them in exogenously. And the main methodology for this is computing. And then what I want to talk today about is that I'm going to show you guys today a model at full scale and ask the question. Well, I'll assert that we don't know really when do we need full scale models. When can we have scaled down models? Can we scale all the way down to just one representative agent? Maybe yes, maybe no. But it may be that between 1 agent and 1 million agents, there's going to be a lot of interesting turf here. So I'd like to raise that at the end. What is the appropriate scale for given a particular model? So the background is that all this material I'm going through today is in this book that's going to come out next year. With everything goes according to Hoyle here. We're still working on figures for the book, but the idea is that we're going to model the entire U.S. private sector. So I don't expect everybody to understand the scale and scope of the private sector, so I'm going to go through it in detail. But we all know that the private sector is composed of firms which have employees, and that you think about this manifests itself in our daily lives, if nothing else, the idea that our investment portfolios, all of us have 401k, 403b accounts, and everything we invest in are the firms in America, right? And I should say I gave a version of this talk recently to an ACM meeting on AI and finance, and of course all of those finance guys say, yeah, of course we need to understand how the firms work, and we were putting all of our we were investing huge amounts of money in those firms, and we need to understand how they work. So what do we know about these firms? Well, I've just described all these competing theories that read like science. They read like philosophy. They're not really falsifiable, all those theories. Yet we have this data universe increasingly available to us. And so we don't have satisfactory models. So the idea is, let's build a model. So first, I'm going to describe the data. I'm going to burn through that and just some summaries. You guys have seen parts of it before, probably. And then we'll talk about a model of it. Okay, so just because not all of you guys are economists, we'll just go through the basic idea that basic calibration that we all get on the same page here. There's a pool of employees, a pool of those employees work in firms. In exchange for the work that the employees contribute, the firms give us wages, right? And there are about 120 million people in this private sector, 120 million employees. This is now a pre-COVID number. Hope to get back there soon, post-COVID. Now, here's a funny footnote back to the data issue. There are 30 million people in the American public sector, of which I am one, by the way, because George Mason's a state university. Many of you if you work for the federal government or you work for state and local government. I'm not sure where FFRDCs, Matt may know, but whether you guys are the public sector or not, because you have to file tax returns, I'm guessing you're probably technically in the private sector. Anyways, there's another 30 million people in the public sector. We don't know a lot about those people just because we don't have access to the tax records. There are 30 million firms now in the private sector, but those 30 million firms, many of them don't have employees. Only 6 million have employees approximately. So basically, it's 120 million people stuffed into 6 million firms. So the average firm size you immediately get is 20 workers per firm. And these 6 million 6 million firms have at least one employee. Now so this means leaves 24 million firms without employees. What are these firms? Well, these are going to be places like farms that have no employees, or if my Axtel consulting firm hires no one in a certain year, then on the IRS I file Schedule C and it's counted as a firm, even though it has no employees. So there's a lot of those entities. By the way, they're very neglectable, though. Those 24 million are neglectable. The gross output of the U.S. economy is $30 trillion. About 98% of that is going to be contained. Is created by these 6 million firms. So these 24 million firms without employees don't produce very much output per capita, per unit. But of those 6 million firms with employees, there's only about 10,000 that are publicly traded. So I put them in this small box here, and there's only going to be always one biggest firm, of course, and today that biggest firm is Walmart, right? So Walmart has over 1 million employees, about 1.5 million employees today. So what Walmart employs about 1% of the whole U.S. workforce, a little more, but it fits into the special category of being publicly traded firms. However, the main point of this slide, though, is to say this is not this is just a snapshot of this economy. In reality, every single month in America, pre-COVID, about 50,000 firms come and go, go out of business, come into business, etc. And some of you will know what happened with COVID is March, April, May, June. This thing petered out. It went to zero, basically. Well, a bunch of firms went under. Although it turns out we don't actually know when firms go under until they file tax returns. But that's a different conversation. But basically, there was almost no firm formation. Nobody was asking the IRS for new tax ID numbers in 2020, in the spring of 2020, early summer of 2020. However, since then, perhaps surprising, perhaps not, since basically the mid part of 2020 until now, there's been huge firm formation. And now, of course, many firms, went under, couldn't survive, but you had to have services still provided, whether it be new restaurants or delivery services or whatever. So there's been a giant flowering of so this 50,000 number is kind of a pre-COVID number, not really active for the last 18 months. But then, of course, in the labor pool side too, there are large fluxes in and out of the category of, say, being unemployed or being out of the labor force altogether. Students are out of the labor force, but students come in summertime, or people will retire out of the labor force. So another 2 million there, 2 million per month. And then, of course, the job-to-job transitions are, in fact, even the largest category here. This is not people changing jobs from one firm to another, 3 million a month. And once again, pre-COVID numbers. And by the way, just as a footnote on kind of like, a monthly sanity check, or you get these jobs numbers periodically from the U.S. government. The job number is actually the difference between two large numbers, right? It says a certain number of people requested unemployment compensation this month, a certain number went off, and those, with a number like 2 million going each direction here, the difference between those is what gets reported. So when you hear a number like, it was 500,000 recently, that's a credible number. But when you hear that the number is something like, 80,000, don't put too much faith in it, because it's the difference between two very large numbers, and so potentially some the number is some error associated with actually reporting it. Anyways, this gives you some sense though about what the character of the whole economy looks like. And now we have data on lots of individual things, and this is just kind of a spectrum of kind of the data that we have. I don't expect you guys to look at the details here. I'm just going to pick some of these at random and go through some of these and say, what do we know about the microscopic structure of U.S. firms when we look at the comprehensive data on all firms? Okay, this is just a time series plot showing in red how many employees there have been in recent 25 years. And you see that kind of gently rising in red up to 120 million number. But notice it kind of moves with the number of companies, and they kind of move together, not exactly, but the average can stay right around 20 employees per firm. COVID, of course, is a big spike here, and it looks different. And then many of you will know the work that I did, once again, back in the post-Sugarscape era there, trying to get data on this. And so there's Walmart has about 1 million employees more now, and there are progressively larger numbers of progressively smaller firms down until the modal firm size is 1. Well fit in log coordinates in this way, with a PDF is sloped nearly -2, not quite but close, the ZIF distribution. And so it turns out whether measure size in that way or size by other ways, size by receipts or other ways, we really get the same story. And in particular, what I have here in the lower left-hand corner is the Lorenz curve, which is a way to usually use to plot income disparity. But here I'm using it to plot what are the sizes of firms. And notice that it's so very skewed here, right? If in fact every firm was the same size, the blue line would fall along the 45-degree diagonal here, but it doesn't, which means that there's, of course, if you read it backwards, it would say that, right, the largest 5% of firms employ about 80% of the workforce. So it's very, very skewed. While the smallest 80% of firms employ about 10% of the workforce, right? So it's obviously once again, a very skewed distribution when it comes to sizes. But in fact, these firm sizes are very stable. They don't change very much. I put 10 years of data here. I've just superimposed the data. And there's only 1 year where there's any kind of real fluctuation. That was 2009 when the financial crisis kind of unfolded. And the inset here just shows that many of the largest firms in America today, Microsoft, FedEx, Intel, Walmart, Home Depot, they've actually grown up to their current size, with 1 million or more agents, quite homogeneously over the last 35, 40 years. As the economy fluctuated up and down, they just grew and grew and grew. So many of the biggest firms in America actually are among the youngest. I'm going to take a drink of water here. Okay, I think I'm going to skip this one just to say there's nothing metaphysical about the firm size distribution. Though different countries can have departures from that, but I'm going to skip that for now. I think I'm going to skip this one too. This just says that when you weight things come out differently. Establishments says one cool thing. McDonald's has got 25,000 establishments. Most firms have one establishment, and there's another power law that for that whole thing. So now this is something where we have data. I don't have a model that explains that. So that's it. I'll come back to that at the end. Productivity. Once again, output per input. These 3 lines refer to whether firms are small in blue, medium in red, or large in green. We basically get distributions with once again log coordinates. Output per worker, basically dollars of output per worker. We have these Pareto tails on these distributions. These are it's normal to talk about what is the average productivity. Here I'm showing you the distribution of productivity, and notice that there are 100 firms in America, roughly, small firms, where there's output of around 10 to the 8th. That's $100 million per worker. Now, what are those firms? And for privacy reasons, we can't go into that. But let's imagine things like LeBron James Inc., right? That kind of thing, right? Where you just gigantic output from a very small workforce. In fact, the output here is so gigantic. Just as the footnote we mentioned, that Walmart is down here. Walmart's one of the big firms, right? And they have high output, high productivity, but not among the highest. If in fact Walmart had the productivity of these 100 firms here, Walmart could run the entire U.S. economy. But we can come back and talk about that at the end. Ages are a fun thing to look at. I said we have very accurate data on ages. What we have here are every colored line is the age distribution of U.S. firms in a different year. So you see many different lines. Basically, this is kind of superimposed on one another. That is, the distribution of firms by age is completely stationary. It has not changed. It doesn't change at all. And then the black dots are a discrete Weibull distribution fit to those data. You see a very nice fit across the entire distribution. Now, there are firms that are older than here. They're just with low probability. Now, I've written here, this is pre-crisis. So pre-financial crisis, we had this beautiful Weibull distribution explaining all these firm age data. And then what happened? Well, in the financial crisis, these are now the years since the financial crisis. The blue line is the purple line. Purple, so your Roy G. Bibb colors, red, orange, yellow, green. So red is the most recent year, then orange, then yellow, then anyways, long story short is there was a systematic departure that happens in post-financial crisis. There was too little firm formation. We had less. This was the default amount of firm formation that happened in the pre-crisis years. Since then, we've had less than that. But what's basically happening is we are on schedule to produce a new Weibull distribution, but it's going to have this shape here where my mouse is. It's going to come down and look like this post-financial crisis, a kind of a gentrification of the American set of firms that's going to happen. So we can see that happening. Easy to forecast that it's happening slowly. Okay, I'm going to just march on here and say quickly that we have a variety of these kind of data. I mean, we have ages are not lifetimes. Ages is what is the age? How old are firms? Lifetimes are how old are firms when they die. Another perfectly smooth distribution of these data with some This is pre-crisis, post-crisis, left and right. From these things, we can compute. What's the probability that a firm dies? We get gross regularities here by firms, by age, and by size. These are all targets we want to hit with our model. Average firm life in America when it's born is 15 years. But the weird thing about firm aging is that as a firm gets older, because its probability of failure falls, it's going to live longer. The longer it gets, the older it's going to get, which is a weird way to think about it. Entrance of firms. We said about 50,000 firms enter a month. That's 500,000 a year. You see the time series. There is an amazing power law associated with firm entrance. That is, there are a small number of firms, one in a million firms when it enters actually with more than 1,000 employees. Very, very weird to think about. And exiting firms are the same way. Exiting firms, we see the time series here for exiting firms, but there's also a power law of exiting firms. Now it turns out that these two power laws for entrance and exit have the same slope, but they are not the ZIF slope, they're a different slope. We don't understand why that is the case. And I'm just going to march forward here. I want to get to the model. So I'm just going to say, we have data on firm growth rates. And when you plot just what is the size of time t over size of time t plus 1, what you find are more gross regularities. This is looking at small, medium, and large firms, different colors. We get a bunch more. And the key is here to have 6 million firms. We have 6 million firms in this database. And so even though any one firm is going to grow erratically, over the full 6 million, we get these nice patterns. Which of the theories of the firm explain that pattern? The answer is none. They all talk about growth. None of them say the growth should have this kind of shape. Job tenure. A few Americans have to keep their job for 25 years, but not very many. A decreasing number. Turnover rate. How does the turnover rate depend on firm age? This is in the data, but what we teased this out fairly recently, but we don't understand why it is. This is now a semi-log plot to make it linear like this, or even things like this. We're able to figure out, as workers get older and older, their actual turnover rate falls. So people are less willing to change their jobs once they're older. Another gross rate. Now this is in log coordinates. Now the trouble is we don't have very many decades of worker age here, but basically it appears to be quasi. The blue are the data, the black is the power law line through the data. Anyways, whole bunch of data. I'm going to just skip most of the rest of the details, but buyer supplier networks have a power law distribution of degrees. The work that Omar Guerrero did on when workers move between firms, there is now going to be this gigantic network of which firms are connected, which are not. And then this network has a bunch of other power law features that are described at length in our book, but I'm going to skip here in the interest of time. And then city sizes. Now, many of you know, in fact, Tim is in the audience. In Tim's dissertation, he worked on city size distributions with the great shelling on this committee. This is Professor Ziff's data, in fact, on how the sizes in America grew. America is kind of an inflating balloon. It had a power law distribution among the top 25 cities in 1790. And the whole thing just inflates here over time. Little dips and doodles along the way, but overall, the whole thing grows this way. This is the Ziff 49 book, I believe. It turns out we plotted the data more recently, and it turns out the red line here is the same plot of Ziff's, but for all the metro and micro MSAs in America, that a little curvature at the end, but the main thing over the biggest 800 or so, the red line is the usual way to plot it. You would say, how many residents are there in a city? The orange line is how many employees are there in a city, almost exactly the same plot. The green line is how many firm locations are there in a city, and the blue line is what if we measure firm size by how many firms there are in a city? And the answer is you get almost exactly the same kind of gross regularity. In fact, if you plot it as a PDF, you can plot all these things as PDFs, and you're going to get the same kind of thing too. The black line is the Pareto slope. Okay, so main thing to say is that for all these data, sizes, ages, productivity, etc., and I skipped all the stuff about firm financials, which are also heavy-tailed. We're basically going to get all these growth. I've just shown you 2 or 3 dozen gross regularities. None of those theories that I mentioned before explain any of these data. Okay, so this is the back to the title of the talk. Kind of, we have so many data in this specific domain, basically, that in essence we have so many data that all the theories are wrong. Okay, now this messed up puzzle here is the idea that I'm going to now describe a model which explains some of the data. Okay, not all the data, some of the data. And the mental model is, here's Watkins Glen in the upper right-hand corner, and here's my kid's HO track in the lower right-hand corner. Let's actually just do something. Let's just kind of let's try to build a model at 1-to-1 scale and see, can we get the same model emanating from the data? Can we get the same data emanating from the model as we have in the real world? So can we get 6 million firms to arise, 3 million job changes every month, et cetera? Can we get Walmart to arise with 1 million employees? And so the question is, what microeconomic specification does this, yes or no? In the interest of time, what I'm going to do, I'm going to just burn through the model quickly. I'm going to just give a very kind of cartoon picture of it. Then I want to get on to just show some of the results, and then also to show how we do the computing. So I think that the version of the model in words is heterogeneous agents who can do more as a team than individuals, but who adapt their behavior to one another, who seek new jobs when they're not happy in the current firm, and they use a social network to find those new jobs. Here's the mathematics of it, but I'm going to skip this in the interest of time. It'll be in the slide deck, and feel free to email me about the details. There is, in fact, a kind of simple view of this thing for a 2-person firm. I'm going to skip the details again, but suffice it to say that we have some new results about how these teams are stable, yes or no. So here's the basic idea: is that we have 5 firms here, A through E, and 13 people working in the firms. And at this time t, it looks like this. At time t plus 1, agent 6 is going to leave firm B and join firm A. Agent 10 is going to join firm B. Agent 9 is going to do a startup, and agent 11 is going to shut down firm D. So at time t plus 1, we have 5 firms again with the same 13 agents, but we have different firms. Right? Firm D has been shut down. Firm F is a startup, and there's different composition for each one of the firms. And so here's the whole thing running, which now many of you have seen this thing run. This is a very old version with 1,000 agents. This is a model running with 1,000 agents forming little proto firms. Every horizontal line is a proto firm. The red dots refer to the workers in the firm. The blue dots refer to the workers in the firm. The red dot is the agent with the most seniority who can do the hiring and firing, etc. And if we had more time to let it run, you'd see these firms growing. I notice that most firms are quite small. If I put my mouse over here, firms of size 1, 2, maybe 6, but then 3, 2, 1, 2, 3, 1, 1. Most firms are quite small. A few firms are large. And so when we first had this model running at this small scale, we realized this model can produce things that are heavy-tailed. That was the good news. Although we had to eventually doctor the parameters to make it all work out. We see a big firm growing here up now. It's another firm declining. Okay. With this set of about a dozen parameters you're seeing here, things having to do with what are the agent's preferences for income, how much increase in returns we build in, with about a dozen parameters now, running it with 120 million agents, we're going to produce results that look a lot like the real world. And that's kind of the punchline about how this model is the beginning of explaining the data. We get 6 million firms to arise. We in log coordinates here. We get about this particular realization about 100,000 firms being born every month. A little bit less than that exiting. Notice there's more volatility on the exits than on the entrances, so that's realistic. Firm size, we're getting the right shape of the firm size distribution coming out. Also for output, and then we get output increases with input. That's a good result. We are getting this over the course of 300 months of the model, about 25 years. We get these waves where a biggest firm will exist at about size 1 million. It'll then decline and be replaced by another big firm, et cetera. So over the course of 25 years, about maybe 6 or 8 big firms dominate this economy, which has an average firm size of 20. That's the blue line. On the left is what the productivity distribution should be. On the right is what we get. It's something similar. It's not exactly the same, but it's in the right ballpark. Firm ages. Every one of these lines is an age distribution in any year. The dots are what comes out of our model. It's kind of close. It's not exactly the same. Growth. We are getting the same kind of growth rate. Some firms decline. Some firms get bigger, and most firms don't change much. It should look like this inset. It doesn't look exactly the same, but looks similar. Job tenure. The data are up top. The model is below. We kind of this model closely agrees with an exponential job tenure distribution. And then labor flow networks. This is Omar's work for his dissertation about who changes jobs when. What's the structure of that graph? Well, this is what comes out of our model. The inset here is what it should look like. And notice that we get a very close agreement with what it should look like when we do it at full scale with what we actually have coming out of the model. Now notice in the real world, the real world's messier. Our model is much cleaner, but it has the right kind of shape to these various network metrics. And then finally, we can also do things with spatial stuff, but I'm skipping it here. Turns out every one of the chapters of the book goes through variations on these things. I'm going to skip that in the interest of time and just kind of get to the punchline here, because we're talking about really kind of scale issues. So since many of you guys have probably not played with models at this scale, let me just mention how we really do it and say how we do it. I'm also try to save you guys some time by saying what didn't work. And so over the course of many years, we found out what didn't work, and things like I'm in Minnesota, so I'll say it. Cray computers don't work because it's all synchronized. Clouds are hard to manage because you can't control the hardware. A lot of languages had a lot of promise. We never could get them to work very well. So we ended up with just a giant machine, single machines with giant flat memory spaces, an OS that handles it, as many processors, as many cores as you can get. And then our code is written in C++ with OpenMP or Intel threaded building blocks as a ways to parallelize it. A machine with a terabyte of RAM, you can get a terabyte of RAM these days for like $25K bucks, maybe $20K dollars, even 100 cores. So you can buy a big workstation today for not that much money. And then this model will now run with 100 million agents. We got it down to about 45 minutes to reach steady state configuration. So how do we do that? We do it by the classical fork join parallelization. The model is rendered with all those agents. Every month we break the agents up into pieces, and every core we say, okay, you agents go out, figure out which firm you want to work in. Then we bring them back together, have them work. Firms then make output in parallel, and then the firms pay the workers and repeat. So by this fork join parallelism, we're able to realize, in fact, 120 million agents in about 45 minutes. Okay, so the summary of all this, and I apologize for taking a little more time than I wanted to, is that none of the conventional theories of the firm can explain any fraction of the data that I've just shown you. So the philosophy we've used in this is to say, let the data guide the model building. That is, have the data be the target. Try to hit those extreme statistics. Try to really make the model have output which matches the input. And we can do that when firms have increasing returns to scale. So our book is going to report a model at full scale with a real U.S. economy in which there are no shocks. There are no exogenous shocks. Everything is endogenous. And people move between firms for good economic reasons. And it turns out that, for a corollary, for those of you who think about equilibrium, that we don't have Nash equilibrium in the model. We have basically Nash disequilibrium. And so just, in those domains where we really have comprehensive microdata. So think, Social Security Administration, USDA, this case of these tax data. Essentially, most social theories are opaque. and do not tell us very much about what that microdata should look like. And so if we build theories that build models that can explain the microdata, we really are going to be off in new theoretical domains altogether. And my sense is, these are going to be domains where things like institutions are going to matter a lot. People are not going to be rational, but rather purposive. And I've written here, just about enough computing to do this today. I mean, without the parallel computing detour, without which I spent about 5 years of my life pursuing, I mean, this model would take 4 or 5 days to run. So it only runs in fast enough by using all the computing we have available to us today. And so the final thing I want to leave you with is just, can we use all these data, all this computing, to create really next generation social theories that are going to, once again, if not exactly prove that all the previous work is not worth much, but it's going to at least, they'll at least maybe subsume the previous theories, or at least move beyond the previous theories into a world where we can say, let's adjudicate the theories based on how well they explain the data, not based on whether they comport with some preconceived notions about what is good social theory. And with that, I'll stop, and hopefully there's at least a couple minutes for questions.
Thank you. That was just phenomenal. Yeah, we actually have plenty of time for questions. So just raise your hand and let's get them going. All right, Dave, you were
All
first.
right. So yeah, it's never happened before. I'm just going to celebrate for a moment. So Rob, you started out saying that this was not for economists, but I quietly listened anyway. I do in fact teach industrial organization, and I can't begin to tell you how frustrating it is to teach theories that don't have anything to support them. So I, from that point of view, I'm getting ready to retire. So you've done nothing to help me. Thank you very much. But my younger colleagues, hopefully, right, will be able to be data informed, and hopefully soon.
Yes.
Because that is very frustrating about the creation of firms, the distribution of firm sizes, all these other attributes that you've been discussing here, have nothing to support them in. And yet, especially in graduate programs, IO is one of the hardest courses. Students frequently say that was the backbreaker of their program, and it's all almost useless.
Yeah, it's kind of like philosophy, right, David? I mean, it's a lot of students have a hard time getting their head around it because it's not maybe that some of the theories even assault their intuition, and my personal feeling is that maybe like the blind men touching the elephant, right? All the theories have a little bit of truth to them, but they all lack a kind of real world relevance, I think.
Well, they do, and we started the day actually with a reference to George E. Box, and of course the one that we all love is that all models are wrong, but some are useful, and certainly the Cournot-Nash equilibrium or something like that. It is informative, but you've accomplished that in 15 minutes, and you're going to spend a whole semester on a course.
Right? Exactly right. That's right. IO should not be a course about applied Nash equilibrium. It should not.
Absolutely. So anyway, I applaud what you're doing. Thank you very much.
Okay, great.
Jacob, please.
Thank you for the fascinating talk. I'm looking forward to reading the book when it comes out. I'm wondering, you said you would talk a little bit about scale and what scale models need to be at. And so one of the things I do is material science education using atomistic models. We have many levels of models where for many properties of materials, you don't need to go to the quantum level of detail. Yeah, so we use models that can't explain the micro level of data, but they're useful. So I'm curious your thoughts on that. Like, can this model be abstracted to have a simpler firm level agent that then can be used in higher level models of the whole economy with trade networks going on, for example?
Understood. Yeah, understood. And so let me just report that, and for those who have sat with me in George Mason for many years, you all will recognize what I'm going to say next. That of course, when we first started off, we couldn't do 10 to the 8th agents, right? We could only do, once again, I showed you the movie for 1,000, and then I think from like 2006 forward or so, 7, we were up to 1 million agents, and then between code optimization and better hardware, et cetera, we got up to 100 million. So it is the case, Jacob, that we certainly spent most of our time using small scale models. So I'll just report two kinds of frustrations with that. First thing to say is there is the very practical frustration associated, I found, with economics referees who said things like they would say, look, you've got tantalizing results with, say, 100,000 or 1 million agents, but I personally, as a referee, don't believe they're going to scale up when you go to full scale. So that was their assertion, right? And there was no way to disprove that assertion until we did it, right? So that's a very practical thing. But then think about here's a more substantive criticism, I think, or a more substantive rationale for the size issue is that think about growth. Firm growth is a fluctuation, and so it turns out it's actually a heavy tail fluctuation here in the real data. So it turns out that we know that the fluctuations are going to scale with the size of the system somehow, right? And so it turns out many of these data that I showed here, many of these data are going to scale as we change. So when we go from 1 million to 10 million to 100 million agents, they're all going to scale. And here's the problem: they're going to scale differently. So it turns out for the many years that we had to work at subscale, sub full scale models, we had to do fairly exotic scaling to say, okay, does the productivity distribution coming out of the model really look like the one coming out of the data? Yes or no? Does the firm sizes coming out of the and so let me just report to you, and I'm sure this will be, since you do condensed matter, this will probably be no surprise to you, Jacob. But when we could finally go to full scale, it was a complete catharsis, because now you say, how do you rescale the data? And the answer is you don't say rescale the data, because the data coming out of the model should be exactly the same as the data coming out of the IRS, right? And so that was such an amazing, I guess that was such an amazing experience, just cognitively, that since we've been able to do this for the last couple of years, I've never actually now had the kind of the guts or gumption or balls, I guess, to go back now and say, okay, let's now start turning the ratchet the other way and say, can I actually, for a different set of parameters, maybe can I still get the right results coming out with only, say, 10 to the 7th agents, or 10, or 5 times 10 to the 6th of them. So that work remains to be done. So I think it's fair to say we don't know a lot today about how to kind of scale up and scale down systems. I mean, my personal bias is, if you try to model a social system, try to run it at full scale, and then now start winding it back and see how much can you still explain with a smaller scale model. I think what's problematical, and what the old Sugarscape model also kind of demonstrated, was that with very small models you just can't say a lot, right? I mean, very small models have a variety of aggregation and other kinds of biases in there, and so But anyways, this is an important research topic. I would invite all of you guys in the audience to we should have research programs mounted at NSF and at DARPA, et cetera, on this. I mean, as ABMs, as computational agents move forward as a research paradigm, we need to better understand that, and today we don't understand much about that.
Van, would you like to take the floor?
Yes, please. Thank you very much, Rob. That was fascinating and very stimulating.
Hey, Van, good to see you.
There is a reason, I think, that a lot of those theories that you listed have traction. And that is that you can write down the basic idea in one line.
Fair enough. Yeah.
What you showed us is a model. You showed us a set of parameters. You didn't show us exactly how those parameters end up working in your model. But at the end of the day, it's not going to be one line.
Exactly.
It's going to be an elevator speech. Do you have a claim here that's sort of hiding in the bushes that says accurate modeling of real world data is beyond the reach of a theory in the classical understood sense of a very concise statement of what's going on? Or do you have some way at the end of your book, within maybe just one paragraph, if not one sentence, to say, here is the theory that we have come up with that does explain the data, that has the comparable economy and parsimony of the theories that you've disproved?
It's a good question, and I think that the short answer, and I'll see what you guys think when you read the book, but it is the case that we can state the model, in one chapter, for example, one chapter. It is the case that so as you said, the model is nowhere near as concise as any of these kind of classical theories of the firm. It is the case that when you think about now, go back to I put up that slide about the standard model in physics. Now, the standard model in physics includes lots of things like quantum field theory, and includes a whole host of fundamental particles, right? I mean, that's also not a model that you can state in one sentence either. So my sense is that the model that we advance for how firms work, how the whole American private sector works, the model that we advance is not more complicated than like the standard model of physics, for example, right? So it's certainly the case that it is more complicated, unfortunately, than these very simple, like, firms profit maximize, right? Or firms economize on transaction costs. But I wonder if these theories here, I think that I used a slightly pejorative word in this up here where I said these theories tend to be simplistic, right? They're almost too simple. It's like many of these theories, and I probably am impolitic when I say it, but many of these theories are like Greek chemistry, right? I mean, this is land, air, water, fire, right? I mean, the world is not so simple, and so our theory is more complex. It is true, but I think that I wonder if when Mendeleev first promulgated the periodic table, I wonder if anybody ever said to him, they said, "Look, it's interesting the way you've done this, but this is too complex. We'll never be able to teach undergraduates how about all these different elements, right?" I don't know.
But to think about the periodic table,
yeah,
you can say in one sentence that you've got rows that indicate increasing atomic number, and you've got columns that indicate how many of the outermost shell electrons are there. Yeah. And that's the theory right there. That fundamental one sentence summary tells you how it works. Now you want the details, I'm going to dive down. But I can tell you that what really matters is the number of free electrons in the outer shell.
Yeah, and so here's my version of that, which I didn't do a good job on it, but basically, you have to have heterogeneous agents in an increasing returns to scale environment who are going to adjust their behavior to one another, who are not going to waste a lot of clock cycles trying to be too rational, and they're going to basically get paid for what they do by look for jobs in the social network. All these things are seem at the moment to be. Well, we demonstrate that they're sufficient. My sense is that there's some necessity for many of these things underlying it, and we do have a model of it. But this is more complicated than the simple ones I showed.
Yeah, that's helpful. That's very helpful.
And that's almost a comprehensive list of things that are assumed away in neoclassical theory.
Ah, fair enough, Tim. That's right. You assume a homogeneous agent, right? You assume no social network, etc. Right? Fair enough. So that's an important way to contrast it. I think that gets back to maybe I showed that table earlier. By the way, this table which contrasts kind of like the complexity view of the world with a simple view of the world. We are going to have a table like this coming out in the Journal of Economic Literature, and let me just tell you, the word "simple" is not going to be permitted to be the one that describes economic theory, and the word "complex" is we're having a fight now about whether we can get complex in there. So that story, there's a long sub story to tell about that. I'm not going to get into right now.
Santiago, you've been very patient.
Thank you. Fascinating talk. One question that I have is, what we've seen is a tremendous success of your model. What hopes do we have for having compositional models rather than monolithic models that have to run with large numbers of agents? If we're dealing in terms, or if we're hoping that we get some sort of emergence, as it happens in the rest of nature.
Yeah.
What would your thoughts be regarding this idea of even nearly decomposable systems from Herbert Simon up to something that is a bit more strongly coupled? But I just want to hear your thoughts about it.
Right. Yeah. And so I probably don't have a very satisfactory answer, Santiago. But I wonder if an answer you find acceptable would go along these lines. That think about how real economies work. And it is the case that today we have 10 to the 8th agents. Okay, but go back to the time of the founding of say the U.S. economy. And I put up that plot earlier of the good Professor Ziff, okay, which some of you may not have seen before. That the economy was Ziffian long before we had a large economy, right? I mean, back then, most firms were very small, mostly family-run firms. Most cities, New York City was 25,000 people, right? Right? Maybe this may be Tim may know. Was it Philadelphia was the biggest city in 1790? I'm not sure, but I guess think about this: the economies of the 1790s and 1840s didn't have things like business cycles. In business cycles, I believe that the current kind of anthropology of business cycles are that until we get things like the wide scale use of fiat money and large scale production, you can't really get things like business cycles to happen. Right, the economy is just So anyway, so there can be a lot of emergent phenomena that happen as a result of scale, and this is actually Philip Anderson, the late Princeton physicist, his paper "More is Different" is important to remember here. Right, is that as things, you can have a system and just double or treble its size. It can now have behavior that it didn't have at a different size, right? And so I think it does seem to be the case when it comes to business cycles, right? We know we have to have a big enough economy to get business cycles. And by the way, if anybody wants to know more about that, there is a nice recent paper by Doan Farmer and company in PNAS about where they get kind of endogenous business cycles that happen for relatively large scale models, and they don't happen in the smaller scale version of the same model, is the way I remember it. Anyways, so at 10 to the 8th agents, we're going to get lots of things happening as I've shown you. Now, if we start scaling this back down to 10 to the 7th or 10 to the 6th, I don't know what will happen. It will still be the case that our model will still have the same kind of connectivity. So a la Herbert-Simon decomposability, non-decomposability. I mean, the same kind of, we still get the same kind of labor flow network. Where there are still workers flowing between jobs with only 1 million agents. The issue that is it's just a much smaller economy, and that much smaller economy just behaves differently, which is a weird thing to think about, right? But I think that once again, we don't understand that very well today, unfortunately.
Tim.
Yeah, I'm gonna go meta for a second. We've been talking a lot about the kind of the way that the field is evolving in this conference, and kind of the history, how it's integrating with other things and such. And I'm wondering if I get you to say a little bit about the history of this set of ideas, and to frame it a little bit, I'll point out that the first white paper version of this is what got me interested beyond interested, electrified about the potential of agent-based modeling. And this was the simplest possible version of this. And it was 21 years ago, I believe, that it went onto the Brookings website just as I showed up at graduate school. And I read it and was just like, oh my God, this it appears to me he has nailed how this works with, a few lines of code. And it turns out that
you saw this version of it, Tim. It was this version of it way back when, right?
Yeah, it was, yeah. And this does so much. Even this stupid little version of it does so much of what you just showed. I mean, it's so much better than everything else. It was just instantly super exciting. If you read it, had any idea what you were reading, you were like, okay, this is awesome. So it's 21 years later, and you're about to finally put out a book with the result in it. And it's been, this has become, everybody's read the paper. It's been around, but it's all been in draft because nobody will publish it even now. Could you talk a little bit about what it takes to get these ideas out into public?
Yeah, and maybe if you'll permit me too, let me do a slight digression. I'm going to tell a story that ties into Santiago's last question a little bit. Is that so I showed this model, in Herbert Simon's office. Herbert Simon died in the spring of 2001. I showed this model to him in the fall of '99, I want to say, in his office, and he got extremely excited about this kind of this modeling approach because it brought in for him. He did not know a lot about agent-based modeling. He knew some. He had the Sugar State book. We dedicated that to him, kind of right, but he didn't know a lot about it. But of course, he knew a lot about organizations. He knew a lot about power laws. He knew a lot about even, in some sense, Herbert Simon invented linked lists, for God's sake. He knew a lot about objects in programming, right? Anyways, to make a long story short is, I want to even I'm going to turn this back and pose it to you as a question, Tim, is that on that day when I showed Herb Simon this particular movie, okay, his immediate reaction was, this is how we, as the economics profession, he's a Nobel Prize winner in economics, right? This is how we, the royal we, should be doing macroeconomics. We should be doing model building with data of this type, et cetera, et cetera, et cetera. He got that within 5 minutes. Okay, I'm reporting that to you now. Now, I'm also going to tell you that, okay, I'm in Minnesota here. If I walk over to the University of Minnesota Econ Department and I show them this, they're going to say, that is nothing, you would never want to do this with macroeconomics. They would say, macroeconomics is a study of one representative agent, one representative firm, and that's how we do macroeconomics, right? And so I want to throw it back to you a little bit and say, why is it that some of us, we have a vision for how we could do things differently than that conventional view? And that people who have the conventional view, they seem really to have a hard time to think that there could be stuff on the right that's not in the middle column here. They have a very hard time thinking that this stuff is real out here somehow, right? And is that because we have not been good at promoting our work? I don't know. Is it because they don't have any experience with computing, that they're mathematicians? Maybe. Is it because they've never looked at the data? I don't know. But I think that you're right. It's been a very long program to get this. And there's one more thing to say about it before I do want to have you answer that, Tim. So think about your answer. But one of the way to say it though is the following: is that when I showed Herb Simon the plot, and I showed Herb Simon that run, and I said, look, we're getting skew firm sizes coming out of this thing. And I said, Professor Simon, what should the distribution of firm sizes be for this to be empirically accurate? And he said, I don't know. So in 1999, we had no microdata.
Right. If Herb Simon didn't know, who knows?
Right. So all those data that I showed you in that summary picture there, I mean, these data really it's taken 20 years to get the data together, really, right? Or a different way to say it, every year we get a new data series. Every year the data series, to some extent, kind of show our model is not perfect, and far from perfect. And so every year we've been making more or less large modifications to the model to make it comport with the data. So, but what we've done in 20 years now is today doable in a much more rapid way in some domains, as you guys have talked about. In some domains we still can't do it, right? But like in finance, you can get a lot of data in other allied areas. But now, if you will permit me, Tim, and I think hopefully you'll be good spirited about it. I mean, what do you think that we can do with our colleagues who don't? How come Herbert Simon can see that so fast, and a lot of people can't?
Well, because Herbert Simon was a genius. I mean, that helps. I think the problem is it's not that hard for little people like me to see it, because I don't have that much investment in the old way of seeing it. I haven't gotten tenure on it. I'm not like I haven't invested my life in a different paradigm.
Well, there's no tyranny of sunk costs then, I guess.
The tyranny of sunk costs. And so the people who are, at the end of their career, already having received accolades his accolades were related, but it takes real courage to look at all the sunk costs and say, oh, that's a better idea. That's what I'm going to do with the next 5 years. I just don't think many people have the intellectual courage and flexibility to do that. And people like Herb Simon, there's a reason why he's venerated.
So, but maybe it's the case that when all of us take our models out of the CSSA and we take our models to the AEA or the American Journal of Sociology, maybe all of us, we hope that our colleagues there are going to accept our ideas for what they really are. But as you just pointed out, it may be that the tyranny of sunk costs is going to be a real problem we have to deal with, and we don't always know that we have to deal with it, right?
Yeah.
All right.
Andy, still got a question?
Still got a question. Thank you very much. That was an awesome talk. I'll get to my point very quickly. So in the AI community, there's this thing called interpretable models.
Yes.
That stems from is this idea that you can build these huge, complicated, deep learning models that no one really knows what's going on. So for us picky humans, we build these simple, say, additive models, which are approximations of the deeper model, so that we can look at them and say, yeah, that seems reasonable. Therefore, the larger AI model is acceptable. I was just wondering, this is really trendy. It's come out in the last 5 years. I just wondered, is there anything like that you've looked at with this? Because like the point that was made earlier was the idea that, it's getting down to those weeds. It's a way to extract, to make a simplistic model from this, maybe using the interpretable model methodologies, and then just using that as a way to sort of help people gain trust in what you've done.
Fair enough, Ed. It's a good question. I would say that it is the case that we've used some. I teach in a department now that has a big body of people working on machine learning, and we have used for many of the data. We have many more. Hopefully, it comes across in my talk that we today have many more data on firms than we have explanations for. So I showed you maybe 2 dozen data, and I explained 1 dozen, but we really have say 6 or 7 dozen gross regularities in data that we've teased out using machine learning techniques. We only can explain 1 or 2 dozen of them. So yes, there are a bunch of things we can do on that point from that perspective. it is the case though that some of the things that some of the gross patterns that we've teased out with machine learning techniques are, as you said, are not readily interpretable. Kind of, what does it mean? Is it just kind of some crude correlation, or does it actually have some deeper meaning? It is the, as you guys in the audience know, who are social scientists. I mean, we do have this kind of default representation in economics of kind of one person, one actor, one decision maker kind of perspective, right? So we do have this kind of, so things are interpretable in some level. I mean, when I say that the model is written as some it can be summarized with a few words here. I mean, this all assumes that every agent is a person, and then a combination of agents makes the firm. I mean, so I think we do have this kind of default logic that, at least my sense is that for the rest of my career, at least, I don't know about the rest of you guys, but for the rest of my career, machine learning and data analytics are so slowly diffusing into economics proper that this idea of methodological individualism and one agent, one person will be the default representation. If in fact, of course, in finance we know better. In finance, there's a whole variety of various black boxes that nobody really understands, but which have some forecasting power, obviously. And so, all the stat arbitrage guys use them on a daily basis, right? I mean, many of our portfolios probably depend on those things, right? But, so I think that you raise an important question. I don't personally have a big investment in one side. How that question gets answered ultimately, I do say though that it does seem to me that when we can posit our models in terms of actual actors making decisions, then they come kind of with an automatic amount of intelligibility, I guess.
Thank you.
Stephen, you've also been very patient.
Hey, Steve, how you doing?
Good, Rob. How are you? Great
Good.
talk. It's wonderful stuff. And as you know, I'm familiar with this and great.
Yep.
So I want to ask a question, and it's a little bit selfish. I'm trying to get my understanding better, but I think that maybe if that it might be just possibly interesting to others as well. So let me give you a slightly different spin on what you've said.
Okay.
And tell me if it's wrong, or and if it is wrong, I'd be grateful for understanding. But what I see from you, it's not simply the data, is that what you're doing is you're endowing the world with these zillions of agents, right? It's individual agent view, individual person view, and you've got a kind of model that's a little more complex than usual, and it in fact includes and you have rules of association as well. That is on this particular slide, and basically you're throwing them together under a certain regime, and then scaling it up like crazy, and let's see what happens. And what you've shown is when you do this, you can adjust you can tweak a little bit what their rules of simple rules of behavior are, and you can tweak a bit, some of the parameters. And when you do this, big things happen. Phases change as you scale up. And when you get to the 120 million agents, that's the same size as our population, it in fact, in many ways, behaves the same. And so you're explaining the data, but what you've done is you're explaining the data as interactions of zillions of small machines interacting with each other. Is that unfair or anything?
It's a fair way to put it, Steve. I think I don't think of it as in that way, but you're right. It's a large number of individual automata, as it were, interactive automata, and I guess the question is to what extent do you find it objectionable if I associate those automata with real people? It's reasonable to say that I, Axtel, don't have the data on what the individual people did. I'm just, of course, getting the right macroscopic properties coming out. So my little machines may, in fact, be, somewhat unlike the real people I'm trying to represent. But I think that your characterization of it is plausible. I mean, your characterization of it is fine.
So I'm all for it. I think it's a great strategy. I mean, I think, part of the surprise here is that something this simple, actually, when it scales up, should have A, the regularity behavior that you see, and B, the regularity behavior that's observed in the real world. That's really kind of remarkable. And so what that does is gives you an explanation, and then if you want to introduce more variation at the micro level, you can see, well, you have to, it nets out about right, so you can push and pull in various different ways, and it gives you a principled scope for complexifying in the direction of further reality the micro agents.
Let me say that a different way too. And would you buy this? That, I've only used this terminology once or twice, so let's see if you buy this. That if in fact somebody wants to add more behavioral features or add more dimensions of something to the model, they want to make the model more elaborate, then it's a little bit it's incumbent on them then to explain more of the data. And I've got more data to explain.
Yeah, there you go.
I just don't
exactly.
Yeah, but this the basic model described here and then described here, with some symbols. This model, it's at least also too, in some sense, this model is not the last word on explaining these firm level microdata. This model, in some sense, just kind of the first word, and of course there'd be lots of subsequent things that can be done with it, presumably. And of course, we're in our book, we're going to make the code available, and there's both a Python version and a C++ version. I mean, back to the scale issue, one of the slight, unfortunate things about the Python version, though, is that you can't realize the Python version with 10 to the 8th agents and have it run in less than a week. I mean, that's unfortunate. Yeah. So that you need to have the C++ version and multiple cores to make it run fast. But I think that your interpretation seems it's a good one, Steve. I think.
Yeah. So I applaud it, of course, but thank you.
Yeah.
Other questions? Dave, you've got your hand up. Is that on purpose?
I never put it down, but as long as it's still up. Yeah. Okay. So not to argue directly with Van, because I sort of had the same reaction, and that is in the sense that, yes, the elegance of the Cournot-Nash equilibrium or the various other models of the Firm, the Bertrand, the Stackelberg, all those things, is that they can be expressed, in a line succinctly and so on. And that's true, except for, and I think Tim mentioned this, all the neoclassical assumptions that are there. And if you're going to code those assumptions, that's a lot of lines, right? And so we all know this in agent-based modeling. Somebody comes to us to a problem they can express in a sentence, and we write hundreds of lines of code to encode their assumption, operationalize it, exactly. And I'm reminded of Murray Gell-Mann's definition of complexity, and that is the word count on the shortest possible description. Right? And once you've included all the assumptions, I am not convinced that many of those classical models are any shorter than what you're doing here.
Fair enough. And then, of course, from a computational complexity point of view, it's usually very hard to even write down rational agents, right? Because they have to do fantastical calculations that are only possible by God, in essence.
Well, yeah, right. And with information only accessible thereby.
Yeah.
Right.
Aaron, please.
So, Rob, you talked a lot about sort of getting the model and ideas into sort of the academic environment and hinted a little bit at the understandability. Could you say any more about your experience in the law dealing sort of more in the policy world of having models that are built out of natural units and not aggregates or other kind of things, and how it's been received more in the applied realm?
Yep. So let me just mention that. So one of the biggest, areas where I think that the model like this can be useful is in macro. But once again, not from the from a neoclassical macro academic economist point of view, but basically, when I've shown this model on several occasions to central bankers, and the central bankers say, we've got a whole bunch of data, and we keep throwing in the garbage can when we estimate these DSG models with one consumer in one firm. Well, why are we doing that? Well, why aren't we using all those data? And in particular, they say, well, couldn't we have a model like this? Couldn't this be the backbone of the industrial manufacturing sector of our macro model or something, right? So it turns out like people at the Bank of England, Andy Haldane in particular. I mean, I've been talking to all those guys about maybe a model like this can become the basis for a new flavor of macro. Now, that's a project that's probably going to take a decade to play out. I mean, some of you guys will know that there are pretty good policy relevant macro models today used in the EU, for example. They're typically smaller scale, so they're not every company in the EU. But this guy Herbert Daoud in particular, the EURACE model, it's something on the order of 10,000 firms, and with 10,000, I mean, he can do a pretty good job of kind of covering the from that skew distribution of size that I showed you guys earlier, right? I mean, a relatively small number of firms hires most of the workforce. So the first thing to say is that there are people who are thinking about there are already kind of small scale models of ABMs for macro that are used for policy for sure. But then I think that maybe think out broadly. I mean, think about the year 2030 or 2050. I mean, if we have all the data, if we have the ability to compute with that easily, why would we not use a macro model grounded in all 6 million firms? I mean, and now you may say, well, there's privacy reasons or other things. Okay, fine. But it does seem like if the more that maybe our friends in basic research in DARPA or NSF could come up with a way to make more data private, et cetera, we really would have a way to utilize all these data for purposes of policy. Which I mean, that seems to me to be would be a holy grail of this kind of approach. And or maybe how about this is a different way to say it. In a world of the world of the year 2100, where there's tens of thousands of cores in every phone, et cetera. I mean, I'm sure there are going to be models that are going to be highly disaggregated of this, which have this broad character, and certainly not going to be the case that we're going to have representative agent model. And it's just impossible to believe that that's going to be the case.
I wonder though, because the problem with a big complex model with all kinds of crazy path dependencies and stuff in it is that for some questions you're going to get whereas with a simpler model you always get an answer. I don't know if the policy world is quite ready for that is not an answerable question and you're not going to get an answer to it.
Fair enough.
Maybe it may need to get used to the idea because that is the way the world is. But yeah.
True. And how about this too? How about maybe something we don't have today? One thing we have today, we have relatively transparent models. I do worry about the following. I do worry about could there be policy entrepreneurs in the future who are not that great economists or modelers, but they have a lot of charisma, right? And they're just about capable enough to kind of jury rig their model to produce interesting, but not necessarily very accurate answers. And could they be a source of future, let's call it kind of trouble? People who are capable, but kind of like they're really going to be good salesmen, but not necessarily good scientists. And I do worry about that. That's a possibility.
We don't need to wait for that one.
That's true. In the DoD world, there has been some of that going on already, right? So
yep.
Without naming names, I guess.
Yeah, way ahead of you on that one. Any other questions or comments?
Thank you guys for the really good comments and questions. Thank you.
Thank you. It was fantastic. Unfortunately, applause is not great, but we've got these silly emojis we can do, which are almost as good. Oh, Jacob.
Yeah, I was wondering if I could ask one more question on the philosophy of science. What is the theory in this case versus the model?
So the theory is that a population of agents with the I'm going to I guess this goes back to that qualitative. So here's the qualitative rendering of it. And the reason why I believe this constitutes a kind of at least some kind of crude theory was that as Tim already mentioned, or someone mentioned, many of these features are not in the conventional neoclassical models, right? So these are things any one of these things can get you kind of thrown out of the American Economic Review. And so now I'm joining together a bunch of them. So this is a model which this is now stated in an abstract way. Now here's the mathematical theory of it, and then here is going to be how here's how I instantiate it, parametrically to actually work, right? I have to have a bunch of parameters. So this is now the model, right? So this is the model instance of this theory, which by the way has a graphical interpretation, et cetera, et cetera. So. But your point is that this is not as simple a theory as the conventional one.
No, that's not my point. It seems to me like then on this view, I mean, this is a question that doesn't just relate to this work. It's a question I have in general. But in this view, it seems like a theory is just sort of an underspecified model. Like you see what I mean?
Yeah. Would you say though that there's a standard model in physics, and we can monkey around with what the speed of light is, but it's still the standard model of physics, right? So is that not kind of the norm there already too? Or not? I don't know.
Yeah, it could be. This is just something I'm trying to clarify.
Yeah, think about what's this. There's a standard model in physics, but then there's the fine structure constant, right? And the fine structure constant depends on a whole bunch of different things, right? Well, phi structure constant, if the phi structure constant was different, we have a very different universe, right? But so there is a standard model. I guess, do you think of the standard model with the parameters or without the parameters? And I think that there's a, right, I mean, physicists normally think about it with a lot of symbols, right? And then you instantiate it with kind of our best guesses for our best current guesses for the parameters, and then you build a model for what happened in the Large Hadron Collider. Does that make sense? I mean, it's something along those lines. But by the way, if you want to learn more about this idea of models as mediators, Morgan and Morse have a nice book about this. And although it's mostly social science specific, you will know that their co-author Nancy Cartwright did a lot of philosophy of physics also. She's the author of How the Laws of Physics Lie. If you haven't seen that book, which is a well-known study in this general area.